In this opportunity, we're gonna discuss about the entropy changes when there is heat transfer between the system and the surroundings. Typically, when we are doing thermochemistry between system and surroundings, usually we keep the surroundings on the shadows because according to the first law of thermodynamics, the changing energy of the universe is equal to zero, which means whatever happens to the system happens to the surroundings with the opposite sign. Now, we are working with entropy, so the story is not so easy because now the changing entropy for the universe is not necessarily zero. Now we are looking at that from the point of view of whenever you have a system, you want to know if that system, in this case a chemical reaction for example, is going to be spontaneous or not. If it's spontaneous, then the changing entropy for the universe, where that system is, then has to be positive, has to be larger than zero. So now the surroundings will have a more active role, if you will, in everything that we're going to discuss when it comes to entropy. Why? Because now whatever happens to the system not necessarily happens to the surroundings. So now the surroundings will have a more active role in determining whether a system, a reaction, or a chemical process is spontaneous or not. Okay? So, as I said before, in order for a process to be spontaneous, the changing entropy for the universe has to be positive. Okay? So, usually, that means that you can even have a system that is going to be, or the changing entropy for that system could be negative, but if it's so that the changing entropy for the surroundings is larger and is positive, then you can still have a spontaneous process. Okay, so that makes processes that from the point of view of thermal energy look like they might be non-spontaneous, then because of the changing entropy for the surroundings is larger, then it's going to be a spontaneous process. For example, let's say when we're looking at this, in this particular case, the condensation of water vapor. Okay, we are looking at that particular case. So remember, if it's condensation, then you are going from the liquid phase. Let's say what we are looking at, condensation of water vapor means you have water in the gas phase going to water in the liquid phase. And based on what we know about entropy to this point, the entropy on the reactant side is larger. So here, entropy of the reactants is larger than the entropy of the products. Therefore, the changing entropy for this particular system is going to be negative. So technically, you might think of, well, this shouldn't be a spontaneous process because the changing entropy of the system is negative, and you are looking for something that is positive. However, that happens spontaneously. So what is the reason for that? Well, remember that if you go in the opposite direction, if you're going from the liquid to the gas phase, you have to add energy. Okay, so think of boiling water. If you're boiling water, you have to heat the water all the way until it's completely evaporated. You had to add energy to that water. The opposite, coming from the gas phase to the liquid phase, has to release energy. Therefore, that release of energy, that energy that is being released when water is condensing, that heat is going into the surroundings, and that heat, the heat that is going into the surroundings then is used to increase the entropy of the surroundings. And if that increase is such that that changing entropy is larger from the surroundings that it is for your reaction, then the process will be spontaneous. Okay? So that happens with the reaction that is exothermic. Okay? Now, in this case, we are going to start working from the quantitative point of view, meaning that we are going to start doing calculations. And what we are one thing that is going to be constant, because has to do with energy, is that the heat. Okay, this is heat. This is not entropy. So this is first law. Okay, whatever happens to the system happens to the surroundings with the opposite sign. That is true for heat exchange, not so much for entropy, but we can use this, right? So therefore, based on that, and with certain given conditions, we can assume that the changing entropy of the surroundings, well, it depends on the heat that the system is either releasing or absorbing, but the relationship is that whenever you're calculating the changing entropy for the surroundings, you have to look at the changing enthalpy for the system, the chemical process, the chemical reaction, whatever it is, and you divide that by the temperature with the opposite sign, and then you obtain the changing entropy for the surroundings. So it's a simple equation. Probably the most confusing part here is that this, I want you to be very clear with this. This is the changing entropy for the surroundings, and it depends on the changing entropy for the system. Let me highlight that with a different color so that it's, hopefully it's a little more clear. Okay, so it's system and surroundings here. So changing entropy for the surroundings, changing enthalpy for the system. Okay, so how do we use this in an equation? So for example, we have this system, right? It's like the combustion of propane. Okay, we have the reaction. As always, whenever you have a chemical reaction, make sure it's balanced. I'm probably gonna give you everything balanced, but just so you know, it's a nice habit that you check that the equation is balanced. Okay, here we have the enthalpy of the reaction. Okay, this equation that we have here, this is the system. Since we are doing chemistry, most likely we are going to be studying chemical reactions. So remember that the enthalpy of the system pretty much is going to be equal to the enthalpy of the reaction. So this for us is going to be synonyms, right? So that enthalpy of reaction is what we're going to use in our equation. So the first question here is, what is the changing entropy for the surroundings? You need temperature here. Now temperature is not going to be a decoration, and because some problems we can give you a temperature but you don't really use it. In this case you are going to use it. One thing that I forgot to mention, this temperature here has to be in Kelvin. And the reason is because you may have temperatures of 0 Celsius degrees, and if you put a 0 in this equation, well, it's not good. Let's put it that way. Okay, so it has to be absolute scale, Kelvin scale. After that, we have to determine what the sign of the entropy change for this system is. And then we are going to determine the changing entropy, the sign of the changing entropy for the universe. Okay. At this time, we are going to do this a little simplified, but bear with me. We're going to go through all of this. Okay. So the first question is calculate the changing entropy for the surroundings, and what is the basically what we have here. So number one, we have 25 degrees that we have to convert that to Kelvin. Okay, so Celsius to Kelvin, you just add 273, so it's 298. Make that a habit. Okay, so it's this case, anything that you're going to be doing with temperature has to be in Kelvin degrees. Okay, so next, what is the equation? The equation for calculating the changing entropy for the surroundings is the negative of the enthalpy of reaction divided by a temperature. So simply, signs matter here. So if your enthalpy has a negative sign, you bring your negative sign here. Okay, it doesn't matter that you already have a negative sign on the equation. That's the negative sign of the equation. You have to bring the sign, whatever it is, that your enthalpy will have, and you divide that by temperature. Okay? One thing that you have to consider here as well is that these units here are kilojoules, And most of the time, what you're gonna see in entropy, sorry, is that the unit is gonna be joules. Okay, this case may not matter that much. Okay, this is 686 kilojoules per Kelvin. Okay, but as you're gonna see later on, the changes in entropy are usually referred as joules per Kelvin. Okay, so as I said, it's a simple calculation. Okay, it's the enthalpy of the reaction divided by the temperature. Once again, this is surroundings, and this is the reaction or the system. So they are pointing in different directions, if you will. So they refer to different compartments when you are looking at the universe. Okay. Now, what is the changing entropy? The sign. We are not calculating the changing entropy for the system just yet. Okay, but we can predict what the sign is. And remember, based on the previous video that you watched, when there are changes of phase, the entropy for a gas is going to be larger than the entropy for a liquid, and the liquid larger than for a solid. If you have a chemical reaction, you can use that to your advantage to predict what the sign of the entropy is. In this particular case, everything is in the gas phase, so you have to look at what side has the larger number of moles of gas, and that will give you an idea of how big is the entropy in that particular case. So if we look at the reactant side, we have 1 mole of propane and 5 moles of oxygen. Those add to 6 moles of gas. And in the product side, we have 3 moles of CO2 and 4 moles of water that add to 7 moles of gas. Okay? Therefore, the entropy of the products, let's just use P, is larger than the entropy of the reactants, and therefore the changing entropy for the reaction is larger than 0. One thing that I forgot to mention here as well is that the sign is positive. Okay, you have a negative enthalpy with a negative sign, they cancel each other. Okay, so you get a positive value. So it turns out that the changing entropy for the system, for the reaction, is also positive. Therefore, remember that the changing entropy for the universe is going to be equal to the changing entropy for the system plus the changing entropy for the surroundings. Okay? But you are adding them together. The changing entropy for the system is positive, the changing entropy for the surroundings is positive. So in this particular case, it's sort of simple. So if they are both positive and you are adding them together, then that sum is also positive. So the changing entropy for the universe, in this particular case, is positive. Okay? Entropy change for the system, positive. Changing entropy for the universe is also positive. Everything is positive in this case. Now, in this case, it's another reaction, and we can do exactly the same thing, right? So we have the changing enthalpy for the reaction. In this case, is positive. Let's highlight that. It's a positive value. So if we are to calculate the changing entropy for this case, then we have, remember, changing entropy of the surroundings is equal to minus delta H of reaction over T. And this is going to be equal to 163. Let me get some more space here. Minus 163.2. I'm going to go ahead and do it in joules. Okay? And just converting this to joules, so you have to multiply by 1000. Okay? And then, since it's 25 Celsius degrees, then 25 times 273, that's 298 Kelvin. Okay? So what you get out of here is, now this was positive, right? We have a positive sign there for the change in enthalpy for the reaction. Therefore, your change in entropy for the surroundings is equal to minus 547.7 joules per Kelvin. Okay, so we have a negative sign here. Now, what is the sign for the system? In the system, then everything is also in the gas phase. Okay, and then we have to count number of moles of gas at both sides of the reaction. So here we have 2 and 1, that's 3, and here we only have 2. So the number of moles on the product side is smaller than the number of moles of gas in the reactant side. Therefore, the change in entropy for the system is less than 0. Okay, you have a larger number of moles of gas on the reactant side. If you decrease the number of moles of gas, then you are decreasing the entropy. Therefore, the change in entropy for the system is going to be negative. And now, if both are negative, since changing entropy of the universe is equal to the sum of those two, and both are negative, okay, then the change in entropy of the universe is also negative. Okay, and what is the requirement for a spontaneous process? The spontaneous process is going to be such that the change in entropy of the universe is positive. Is that the case here? No, the change in entropy of the universe is negative. Therefore, the process is non-spontaneous. Okay, so this is a process that is non-spontaneous. That is an endothermic reaction, is just pure coincidence. So you need to do some intervention in this process in order to happen. Okay, you have to provide some input. Usually you need to provide energy for this to happen, beyond the fact that it is an endothermic reaction. Okay. Now here, this is a little more advanced problem. We have the change in enthalpy for the reaction, minus 107 kilojoules, and now we have the change in entropy for the reaction, which is 285. Okay? However, the question is, at what temperature is the change in entropy for the reaction equal to the change in entropy for the surroundings? So let's focus our attention on this phrase. The change in entropy for the reaction equal to the change in entropy for the surroundings. So basically what we are saying there is that the change in entropy, let's write it up here. The change in entropy for the surroundings is equal to the change in entropy for the reaction. And since the change in entropy for the reaction is equal to 285, that's exactly what we are saying here. 285 joules per Kelvin. Okay, so we are setting the change in entropy for the surroundings equal to 285 joules per Kelvin. So that's pretty much what we're doing here. Okay. However, we want to know at what temperature that happens. So for that particular reason, then we have to remember what our question is, correct? So the change in entropy for the surroundings is equal to minus delta H of reaction over T. So technically, we have the enthalpy of the reaction and we have the change in entropy for the surroundings because we already said that the value for the change in entropy of the surrounding has to be 285. Why 285? Because we want to know when the change in entropy for the surroundings is equal to the change in entropy for the reaction. So technically, all we have to do is solve for T. Therefore, T is equal to minus the change in enthalpy for the reaction divided by the change in entropy for the surroundings. Okay, so T is equal to minus 107, and I'm gonna go ahead since I have units of joules on the changing entropy, then I'm going to change the enthalpy to joules. So this is 107 times 1000 joules, okay? And it's negative. Let's not forget that. It's negative, okay? And the changing entropy of the surroundings is 285 joules per Kelvin. Now, since you have a negative sign in front and a negative sign inside the parentheses, they cancel each other, so you're going to obtain something that is positive. Since we are using the absolute scale, all temperatures are going to be positive, so just double check that that's the case. So you should obtain a positive value here. And joules with joules cancel, and you will end up with units of of Kelvin. So in this case, the result here is 375.4 Kelvin. Okay, here there is not specifying in what unit you are supposed to report your result here, but 375.4 Kelvin, they are equal to 102.3 Celsius, just in case. Okay, just pay attention to what the question, if the particular question is asking you, report your value on Celsius or Kelvin. Okay, so this is a little more at the theoretical level to understand what is going on here, right? So basically, in a process that is exothermic, that heat that is being released is being used to heat up the surroundings. So if they are cool and you are heating up, then you are increasing the thermal energy, you are increasing the energy of the system, and the effect that that has overall is to increase the entropy of those surroundings. Okay, and remember, remember that energy will have larger impact depending on at what temperature the surroundings is at a given time. So, for example, freezing of water in this particular case. If you put a cup of water and put it over on the counter, okay, on the table, and it's room temperature, the water is never gonna freeze. It's not a spontaneous process at that temperature. But if you decrease the temperature then to 0 or below 0, then the water will freeze. So it's spontaneous in that case. Okay? So in the process of freezing water, pretty much the same as when water gas is condensed into liquid form. That's an exothermic process. It's a process that is releasing energy. You might not see it like it's releasing, but you need to remove energy out of the water in order for water to freeze. So that heat that is being released or being extracted is used to heat up the surroundings, and it might be a difficult concept to grasp, but that is what is going on here. Okay, so technically the water is freezing at 0 or below because the heat that is being released from the water is being used to heat the surroundings, and that contributes to increase the entropy of the surroundings, and that's what makes the process spontaneous at that particular temperature. Now, there is a temperature dependent on whether a process is spontaneous or not. Okay? So if we want to look at this in a graphical view, okay? So we are focusing our attention on the enthalpy of the universe, right? So whenever the changing entropy for the universe is positive, the process is going to be spontaneous. Okay, so that's what you are trying to focus your attention here. So the process is spontaneous if the changing entropy for the universe is positive. And that opens the possibility to pretty much anything. So any combination of changing entropy for the system and changing entropy of the surroundings can lead to a spontaneous or non-spontaneous process. It doesn't matter what the values are. What matter is that when you add them together, if the result is positive, it's going to be spontaneous. That means in this case, this system, let's not just write that. This changing entropy for the system is negative. Okay, and the changing entropy for the surroundings is positive. But in this case, if the absolute value, if that changing entropy for the surroundings is much larger, the absolute value is larger than that of the system, you will end up with a changing entropy of the universe that is going to be positive. Okay, and however, if this is still positive, okay, the changing entropy for the surroundings, this is still positive. And here, this is the changing entropy for the system is still negative. However, the magnitude here, this height, if you will, here, is smaller than this one. Okay, so the changing entropy for the system here is much more negative than what the entropy of the surroundings is positive, and therefore you end up with a changing entropy for the universe that is negative. That is a non-spontaneous process. Okay, it requires some intervention for that process to happen. If this refers to the freezing of water, okay, here we are at higher temperature, and higher temperature, lower temperature is a relative term. It's going to be controlled by that equation that we saw before, you know, a changing entropy of the surroundings equal minus delta H over T. Okay, it's regarding to that equation. High temperature, in this particular case for water freezing, high temperature is larger than 0 Celsius, and of course low temperature is less than 0 Celsius. Okay? However, I want you to keep in mind, this is really important. It is not always based on 0 Celsius. It will depend on the system. Okay, there are easily, we're gonna be working with cases in which high temperature means, let's do it more dramatic. There are systems in which low temperature means anything under 800 Celsius degrees. Okay, so you might think, okay, how is that low? Well, it's low for that particular system. That system might not be spontaneous if you are below that temperature, and it will become spontaneous as you go above that temperature. Right now, don't worry too much. We're gonna get that in due time, but this is the meaning behind this. So it's controlled, everything is controlled by entropy and enthalpy. Okay, and those relative values will dictate whether the process is spontaneous or not. Okay? So do not forget about this equation, okay? This is entropy. There is nothing to tell you that the changing entropy for the universe has to be 0. It could be positive, it could be negative, it could be anything, okay? But the important thing here is that in order to be spontaneous, the changing entropy for the universe has to be positive, okay? Any combination of entropy of the system and entropy of the surroundings will do. But as long as when you add them together, you end up with a positive value, you will have a spontaneous process.